For 100 years, we told ourselves a simple story. The story of a hunter and its prey. But in the quiet of the labs, the fossils began to speak. And they told a different story. We saw the scars of battles won. We saw a fortress of bone and muscle. We saw a titan that bent the landscape to its will. What if the most famous victim in history was actually the ultimate survivor? Now, using the power of artificial intelligence, we are not just digging up bones. We are resurrecting a legend. This isn't the story you think you know. This is Triceratops, rebuilt from the code of life itself. Your journey begins in the dust of the American West. You stand in the Hell Creek Formation, a place where the bones of giants sleep just beneath your feet. 66 million years ago, this was a different world, but the story of its discovery begins much more recently, in an age of steam and steel. Imagine the late 1800s, a time of bitter rivalry, when fossil hunters raced to unearth the next great prehistoric monster. They find a pair of massive horns attached to a piece of skull. The first thought? This must be some colossal, extinct bison, a relic from the Ice Age. But they were wrong. Soon, more complete skulls emerged from the rock, and the truth became undeniable. This was no mammal. This was something else entirely. Something reptilian. They gave it a name that echoed with power: Triceratops horridus, the three-horned face. It's a name that feels less like a scientific label and more like the title of a mythological beast. As you look at the fossil, you understand why. The skull is its icon, a masterpiece of biological engineering, nearly a third the length of its entire body. You see the two immense brow horns, each over a meter long, curving forward into lethal points. You see the smaller, stout horn on its nose. But it's the frill that truly dominates. A solid shield of bone flaring up and back from the skull, a defensive wall that protected its vulnerable neck. For decades, we could only marvel at these fossils mounted in museums, static and silent. But now, you watch as a new kind of discovery unfolds. A robotic arm, guided by a scientist, sweeps a beam of light across the ancient bone. This is photogrammetry. Thousands of high-definition photographs are taken, each one capturing a tiny fraction of the whole. At the same time, 3D scanners map every crack, every groove, every detail down to the micron. On a screen beside the fossil, you see a ghost begin to appear, a shimmering cloud of millions of data points slowly coalescing. An algorithm takes over, stitching the images and data together, and the skull is reborn in digital space. You can fly around it, through it, see it from angles the original fossil hunters could only dream of. This digital blueprint allows us to move beyond the what and start to ask how. How did this incredible structure function? From this digital skull, the rest of the skeleton is assembled. You see the immense barrel-chested torso, a fermentation vat designed to process the toughest plant matter. The powerful, pillar-like legs, built not for speed, but for stability and strength, holding up a body that weighed as much as 2 elephants. And at the front, you don't see teeth for chewing, but a sharp, turtle-like beak, a perfect tool for shearing through cycads and ferns. The ancient blueprint is complete. A 9-ton herbivore built like a walking fortress. And now that we have its body, we can resurrect its world. With the digital blueprint assembled, the next step in this resurrection is to rebuild its home. You are no longer in a lab. You're standing on the floodplains of late Cretaceous North America, 66 million years ago. The air is thick, warm, and humid, like a greenhouse. There are no ice caps at the poles, and the world is lush with life. The great inland sea that once split the continent in two has receded, leaving behind a swampy, coastal plain crisscrossed by rivers. This is the world of Triceratops, and for a long time, we could only imagine it. Now, we can reconstruct it, atom by atom. How? The secret is locked inside the very teeth of the animal you see before you. On the screen, you zoom in on the enamel of a fossilized tooth, past the bone, down to the molecular level. Here, scientists perform a kind of chemical time travel called isotopy analysis. The oxygen atoms trapped in the enamel hold a precise record of the water the Triceratops drank, telling us about the temperature and rainfall of its environment. The carbon isotopes reveal the types of plants it was eating. Every bite it took, every sip of water left a permanent signature in its own body. This data, gleaned from the fossil itself, provides the fundamental rules for the world we are about to build. You watch as this raw chemical data is fed into a new kind of software, an ecosystem simulator powered by artificial intelligence. The AI doesn't guess. It takes the isotopic evidence for temperature, humidity, and plant life and uses it to grow a virtual world. On the screen,
River.
A landscape
Cycad.
Materializes. Vast
Temperature.
Forests of ferns, cycads, and magnolias spread across the plains. Rivers, programmed with the ancient climate data, carve their way to the sea. The AI populates this world with the correct flora, creating a scientifically accurate digital environment, a prehistoric nature reserve built from code. This isn't an artist's impression, it's a data-driven reality. Now, other inhabitants begin to appear in this lost world. You see a low-slung armored tank of a dinosaur, Ankylosaurus, its back covered in bony plates, and its tail armed with a devastating club. In the distance, a herd of duck-billed Edmontosaurus, hundreds strong, moves through the swampland, their calls echoing through the trees. Smaller, bipedal dinosaurs dart through the undergrowth. This was a world of giants, a complex web of life where Triceratops was not just a resident, but a cornerstone of the ecosystem. It was a primary landscape shaper, a 9-ton lawnmower clearing paths through the dense vegetation. But every ecosystem needs balance, and in this world, that balance is maintained by a predator that has become a legend. You don't see it yet, but you feel its presence. A sudden hush falls over the smaller animals. A deep, resonant tremor vibrates through the ground. The ultimate test of the Triceratops's design is coming. The tremor in the ground intensifies, and through the giant ferns, the apex predator emerges. Tyrannosaurus rex dog. You see it in all its terrifying magnificence. A predator the size of a bus, with a jaw capable of crushing bone. For a century, this was the moment the story ended for Triceratops. But you watch as the 9-ton herbivore turns to face the threat. It lowers its head, presenting a near impenetrable wall of horn and shield. This is not a predator and its prey. This is a standoff between two titans, the irresistible force meeting the immovable object. And for the first time, we can truly analyze the physics of this legendary encounter. The scene freezes and shifts back to the digital lab. The 3D model of the Triceratops skull from Act 1 is now loaded into a new program, a biomechanical simulator. This is the same kind of software engineers use to stress test jet engines and design crash-resistant cars. On the screen, a virtual T-Rex jaw clamps down on the digital frill. You see a wave of color spread across the model, illustrating the stress forces. Blue and green show where the frill easily dissipates the energy, but lines of yellow and red show the points of potential failure. The simulation confirms the frill isn't just for show. It's a shield, brilliantly engineered to absorb and redirect the most powerful bite force the world has ever known. Next, the model simulates a charge. How much force could those horns generate? The data is stunning. The skull acts as a perfect shock absorber, allowing the Triceratops to put its entire 9 tons of body weight behind a devastating ramming attack. This isn't just theory. The proof is etched into the bones themselves. You see a real fossil, a section of a Triceratops squamosal, part of the frill, being loaded into a medical CT scanner. As the machine whirs, hundreds of X-ray images are taken, digitally slicing through the ancient bone. On the monitor, a 3D reconstruction of the fossil appears, one that allows you to see inside. And there it is, a deep, circular puncture wound that has healed over. The bone grew back around the injury, meaning this animal survived the encounter. Scientists can digitally match this hole to its cause, and the fit is perfect, the conical tooth of a Tyrannosaurus. This is the ultimate evidence, a battle scar that tells a story of survival. Triceratops didn't just fight T-Rex, it won. But its life was more than a series of battles. Evidence from bone beds, where multiple individuals are found fossilized together, suggests a complex social life. You now see a whole herd moving across the plains. They are communicating, perhaps through low-frequency rumbles or visual displays of their magnificent frills. The young are kept safe in the center of the group, a moving fortress of horns. You see them grazing, using their powerful beaks to snap through tough cycads, their cheeks full of food as they process the fibrous vegetation. You are witnessing a creature that was a master of its world, a social, powerful, and ultimately successful animal that thrived for millions of years. It was one of the last and greatest of its kind, a true survivor at the very end of the age of dinosaurs. For all its fame, the life of the Triceratops has been shrouded in mystery. Its very identity has been questioned. For years, a debate raged in the world of paleontology. Another large horned dinosaur named Torosaurus, known for having 2 large openings in its frill, was thought by some to be the final adult form of Triceratops. Was the icon we all know and love simply a teenager? To solve this, scientists turned from shovels and brushes to a powerful new tool, machine learning. You see a vast digital library of horned dinosaur skulls on the screen. Every known specimen, from the smallest juveniles to the largest adults, has been 3D scanned. A machine learning algorithm is now tasked with making sense of this immense dataset. It measures hundreds of points on each skull, tracking the subtle changes in horn shape, frill size, and bone texture. The AI begins to sort the skulls, not by name, but by age, creating a continuous growth trajectory. The result is a clear pattern. The algorithm shows that Triceratops followed a distinct path of growth, and Torosaurus another. The AI, by seeing patterns no human eye could discern, has given us our answer. Triceratops is not a juvenile anything. It is its own magnificent, distinct titan. This is the power of our new technological toolkit. It allows us to see the entire life of an animal that has been extinct for 66 million years. And the story of Triceratops has a unique and poignant ending. Its fossils are found in the highest layers of rock from the age of dinosaurs. It was one of the last of its kind, a true final survivor. It lived right up to the final curtain call, grazing in the shadow of the day the sky fell. It may well have been one of the last dinosaurs to ever witness a Cretaceous sunrise. Its legacy is one of resilience, a species that perfected its design and thrived until the very end. And so, our journey of digital resurrection reaches its climax. All the data streams now converge. The 3D skeletal blueprint, the isotopic climate data, the biomechanical force models, and the machine learning growth patterns are all fed into a deep learning network. This AI has studied the movement of modern rhinos and elephants. It understands the physics of weight and momentum, and it has learned the rules of the Cretaceous world we built. On the screen before you, the final miracle happens. The digital skeleton is layered with muscle, sinew, and skin. The AI breathes life into the model. You see it move, not as a puppet, but as a simulated animal. It takes a step, and the ground shakes with the correct force calculated from its biomechanics. It breathes, and its chest expands in the humid air generated from the climate data. This is the digital twin, a ghost from deep time given form and motion by code. We didn't just rebuild a monster, we resurrected an animal. We began with a fragment of bone buried in the dust, a silent relic of a lost world. Through technology, we have pieced it together, understood its strength, rebuilt its environment, and uncovered the secrets of its life. This digital resurrection shows us that Triceratops was never just a victim. It was a warrior, a survivor, and one of the most successful animals of all time. Artificial intelligence is becoming the most powerful tool in the paleontologist's kit, a time machine built not of gears and steel, but of data and algorithms. It allows us to bridge the 66 million year gap and walk with giants once more, seeing them not as fossils, but as the magnificent living creatures they once were.